As we start this unit on 3D vectors, let's talk about, first of all, the three-dimensional space that we're going to be working in, okay? Now, we're used to dealing with the Cartesian coordinate system. What we're looking at here is an extension of that Cartesian coordinate system that adds a third axis. Now, something that can be a little bit tricky is to remember which axis goes where. All right? So basically what we've taken is we've taken the XY plane, okay, and we've kind of laid it down on its face. Okay? So here is the x-axis. And we use this dotted line to kind of represent the negative side, or you could say the back side of this three-dimensional space. By the way, you don't have to be an incredible artist to be able to work in 3D, but if you're not, you may actually learn a little bit about dealing with perspective as you do this, okay?
Whoa. Ow. Whoa. Ow. Ow. Oh. Oh.
Are you okay?
I don't know. I really hurt.
You good? What did you like?
April Fools.
Nice. So you're one of those, huh? Thought you passed out on me. I've had that happen, that's the thing. Oh, man. I had a girl with diabetes and the insulin pump and everything. And I had her for, well, I taught her 7th through 12th grade. I had her 6 years straight. So I eventually got to know her pretty well, but first few years were a little bit rough. I never quite knew which her was going to show up, but nice one. All right. All right. All right, so we've got our x-axis that's kind of moving from the back towards you, okay? The negative side is kind of in the background. Positive is moving towards you. Part of the reason why this is tricky is because now the y-axis is kind of going from left to right. All right, so here's our positive y-axis. Okay. There's our positive y-axis to the right, the negative is to the left. Okay? So you can see this. This has kind of been moved towards us forward. All right? While this has kind of been laid down on its side. Then we have the z-axis. The z-axis, our third dimension, adds that element of depth to the situation. Okay? Now the z is kind of easy to remember because up is positive and down is negative. Okay? Now, plotting points can be a challenge. And this is where your artistic ability might be, if you have some, it might be helpful, and if you don't have some, it might be a challenge, but that's all right, because I don't have much artistic ability either, but even I can do this, so it just takes some getting used to. So, we have here, instead of just the intersection of two lines that forms a Cartesian plane, we actually have the intersection of three planes that creates three-dimensional space. Okay? So you see here, the y-axis and the z-axis create this plane, YOZ, and O is our origin. Okay? The x and y axis, this is the plane we're used to working in. Okay, this is that two-dimensional plane that we're used to working with. It's been laid down on its face. But then we also have this XOZ axis, that third plane that defines this space, okay? So, let's look at graphing some of these and give you guys an opportunity to practice a couple, okay?
What the?
Alright, so, if I want to graph the point 2, 3, negative 4, alright, here's my X, Y, and Z axis. Everyone just watch for this one. If I'm graphing this, I need to go 2 units in the X direction, 3 units in the Y direction, and negative 4 units in the Z direction, okay? But getting this to look right can be a challenge, alright? So here I have 2 units in the X direction. Then, and this is where maybe using your pencil or something to help you measure would be helpful, I need to go this far to the right, but I need to do it from where I left off here, okay? You can kind of see the graphing these points as you're dealing with vectors, okay?
Vector addition.
Kind of, yeah, kind of like that. 2 units in the X direction. Now we have 3 units in the Y direction. And then we've got 4 units in the Z direction. So, you know, you could use your pencil or something to kind of measure how far that would be. But we're going to go from where we left off. Okay? So you can see here, you know, we're going straight down from where we left off there. Here we were going straight out, parallel to the y-axis, from where we had left off with our x. And now we have our point 2, 3, negative 4. Okay? Now, I know I'm working on the computer, so it's nice I can, you know, draw it and then drag it over to where I need it to be. But you can do that, you can do this even without a computer, just by measuring. Okay? Let's say I have the point 4, 5, 6. Alright, so first of all, I'm going to come 4 units out on my x-axis. Okay? So there's 4. And then on the y-axis, going a positive 5. 1, 2, 3, 4, 5. So I'm going to measure that distance. Oh, that's convenient. And I'm going to go from where I left off on the x, and that's going to put me right about here. Okay? So here's 5 units on the y. Here's 4 units on the x. Then I need 6 up on my z-axis. 1, 2, 3, 4, 5, 6. That's 6 units. Okay? So from where I left off, that's going to put me right about here. Okay? So however you measure it, it doesn't have to be exact, but it should be close. Draw it on your axis and then measure it up. Okay? So here is z equals 6, then I'm going up. So here's my point, 4, 5, 6. Okay? You're getting the hang of it? Kinda? Now, the reason why it's important to label your axes and stuff like this is because it's real easy. I mean, if I just put a point here, you know, where is that in space, you know? That point could be like here and then straight up, you know, and y is 0. Or I could have gone, you know, here and then over here and then up. Okay? Or I could have gone, you know, all the way out here, and then y was positive, and then I went up. Okay? You don't really know, it's not as obvious as in 2 dimensions, because, you know, we're trying to deal with 3 dimensions on a 2-dimensional piece of paper. Okay? So it's important to label things as you're graphing them. Alright? Try this one. 3, 5, 1. Okay? Point Q is the point 3, 5, 1. Everyone try sketching it. I want to see how you can do.
Here for the Z, that's how far you want it to be above there. Because you did your X and your Y, so you're only going to go up 1 unit from there.
No, okay.
Yeah.
I just drew this really badly, but yeah.
No, that's
I was
all right.
trying to
That's
make sense.
good. Good. Yeah, that'll work.
Do you draw the resultant sign?
The what?
Do you draw the resultant side?
Oh, you're talking about like make it a position vector?
The triangle.
No, you don't need to draw a triangle or anything. We're just plotting a point here.
Oh, okay.
Yeah, we're just plotting a point in this case.
I think you went down 1 instead of up 1 for your last part.
Yeah, positive 1 for your Z. Yeah, that'll work. There we go. That works. Good.
Oh, you know what, actually though? Well, when you did your X, you were on the negative Z axis, rather than going along the X axis.
Oh, yeah. Oh.
Yeah.
It's not.
That's good, Marco.
All right. Did you get it?
Okay. All right, that's, you're getting the idea, although you've got your axes mixed up. Okay? This is your X. You made that your Y. And this should be the Y. And then the up and down one is Z. Okay? So, and your coordinates go in order X, Y, Z. Alright, so 3 is the X, 5 is the Y, 1 is the Z. Okay?
Alright, so if I'm graphing 3, 5, 1, 1, 2, 3 units this way, 1, 2, 3, 4, 5 units on the Y, so that distance to here puts me about there, okay? So I've come over 5 units on the Y, and then my Z, I'm going up 1, it's going to put me about there, alright? Now, guys, these little lines that I'm drawing aren't part of the actual point. Those are just kind of,
Help you find the
you know, it's like Google Maps here. This is the path I'm going to take to get to my point, alright? The point is what we really care about. That's point Q, which is 3, 5, 1. Okay? The rest of it is just how we can help ourselves get to the path. Alright, so that's how we graph, alright?
Can I draw a square to find the point like this?
Yeah, if you want to do that, that'll work. Yeah, I can make a little box. Sure, that works. Luis was just showing me what he did here that helped. And actually mine looks like it's a little bit short. But if it helps to kind of make a three-dimensional box like this, okay, you got that, and then he went like up here on both of these for the 1, and then you know, you can kind of see he made a prism there, a three-dimensional box to kind of find that spot. That can help too. So if it helps you to see that, to visualize it that way, that's fine, okay? Just make sure it's clear what point is your final point, alright? Alright, so there's our XYZ space that we're dealing with. The points, and I guess I didn't really mention this, but all of you picked up on it kind of intuitively that the coordinates are X, Y, and then Z.
It says it right there in the example.
Okay. Oh yeah, there we go. So I did give it to you. They're X, Y, and Z. And this actually is kind of cool because there's so many similarities between 2D and 3D. Most of the stuff that you're going to be working with is exactly the same as two-dimensional. We're just putting in this Z component to it. So, as an example, we're looking at, if we look at unit vectors, okay? Unit vectors. You've seen I and J, which in 2 dimensions were this, okay? These are unit vectors because they have a magnitude of 1, and here it's just in the X direction, here it's just in the Y direction. Well, in 3 dimensions, we still want it to have a magnitude of 1, so their Z component here is 0. And then we have this K unit vector. So we have I, J, and K, and it's 0, 0, 1. Okay, 1 unit in the Z direction. Okay? So that's a similarity. We just put on that third component. Okay? So then if I'm trying to write a vector in unit vector form, okay, I can use the parentheses like we've done before. I can use the parentheses like this. I can also use the angled brackets like this. But if I'm using the unit vector notation, it would just be my horizontal component times I plus my vertical component times J plus my Z or my depth or whatever you want to call that component times K. Alright? So xi plus yj plus zk. Yes?
How would the magnitude work? With
We're gonna get to we're gonna look at all those formulas, all the, angle between vectors, dot product, magnitude, all that stuff. How to find a unit vector in a specific direction. We're gonna apply all of those things to 3D. So that's what we're gonna do over the next couple of days, actually.
question.
Now, our position vector, from the origin to the point, we can write a point as a position vector. So if our point is the point 2, 3, negative 4, I can write position vector OP as 2, 3, negative 4. Okay? Or 2i plus 3j minus 4k. Okay? So again, very similar to what we've done in 2 dimensions. We just have that third component now. Any questions so far? Pretty straightforward. All right, so now, let's say we have the vector between 2 points, okay? Now, if you remember, when we were finding the vector between 2 points in 2 dimensions, we took the coordinate of the point that we were going to, and we subtracted the coordinate of the point we were coming from, right? Or we just thought in terms of rise over run, or rise and run, and how much am I moving to get from one point to another? Well, if I have 2 points in space, I'm going to do the same thing. I'm going to take the coordinates of the point I'm going to and subtract the coordinates of the point I'm coming from. All right? You can think of it as the position vector OB minus the position vector OA, if you like formulas like that. So just as an example, let's say I have point A, that is the point 3, 7, negative 5, and point B is the point 5, negative 4, 11. Okay? If I want vector AB, and remember we would call this the position vector of B relative to A. Okay? We're finding our B's position relative to wherever A is. We're going to take, and this is where this notation is helpful, we're going to take point B, 5, negative 4, and 11, and we're going to subtract the coordinates of point A, 3, 7, and a negative 5. Okay? So, vector AB is the vector 2, negative 11, 16. Okay? Again, you can use logic here. To go from 3 to 5, I have to go a positive 2 in my x's. On my y's, to go from 7 all the way down to 4, I've got to go a negative 11. On my z's, to go from negative 5 all the way up to 11, I've got to go a positive 16. So whether you're thinking of it logically or using the formula, you get the same results here. Okay? And by the way, I know we didn't use this notation as much, but in this unit particularly, when we're doing more operations and things, it can be helpful to use this notation because it gives you a little bit of space to work. And you're not having to like put commas in there, and it's easier to see where one component ends and the next one starts. Okay? So that's one thing. Again, it's just the formula from 2 dimensions, and we have the third dimension thrown in. Okay? Now, again, make sure you're aware of this term. Position vector is one of our vocabulary. Okay? But here we have the position vector of B relative to where A is. That's what vector AB is. Okay? One other thing. What would vector BA be?
Position vector of A relative to B.
Okay, it's a position vector of A relative to B.
And then we negative 2, 11.
Okay. It's the opposite, right? It would be negative 2, positive 11, negative 16. Good. It's the opposite direction, so that idea still applies here. You just take the negative of each of the components. Okay? Now, to answer a question that was brought up earlier, how do we find the magnitude? Okay? How do we find the magnitude? This actually, what you see here in this square root, that's actually our distance formula in 3 dimensions. Okay? Now, like this says, this is the distance between points A and B, which also gives us, also gives us the magnitude of vector AB. Now, once you've figured out what this vector is, you know, if this is your A, B, and C, okay, really all you're doing here is the magnitude of vector AB is the square root of A squared plus B squared plus C squared. Okay? So again, it's just an extension. A squared plus B squared was in the magnitude of AB when it was 2 dimensions. Now we just have the plus 3 or plus C squared. Okay? So, if we think about the example we've been working through here, if I ask you for the magnitude of AB in this case, what are you going to do?
-2 squared plus 1 plus 16 squared.
Okay? Well, for A, it doesn't matter because opposite have the same magnitude,
Well,
but
I've added.
for AB, we'd have 2 squared plus negative 11 squared plus 16 squared, and then it would be all square rooted. Okay? So we have 4 plus 121 plus 256. That's 381. Okay? I know that's divisible by 3. I don't know if that'll help us. That'd be 127.
Yeah,
And that's not divisible by 3 again. I think 127 might be prime even. But anyways, what is that approximately as a decimal?
19.52.
19.52.
Just move the equal sign over to the. There we go.
19.52. There we go. Okay, so that's the magnitude of that vector AB. Okay? Now, here's another one. Try this one on your own. Find vector AB. Try sketching the points first, then find vector AB, then find the magnitude of vector AB.
And then one.
Huh?
And then one.
Well, and then, just like we did with 2 dimensions, we're going to use the magnitude for different applications.
But wait, there's more.
Yep. Okay, so let's see here. For vector AB, what are your components?
-4, -3, 5.
-4, -3, and 5. So this vector here is going from the right to the left, or I'm sorry, from front to back. That's why x is negative. It's kind of going back 4 units. It's going 3 units to the left. That's our y-axis, so going left to right. But then it's going 5 units up. Now, if you just look at this without seeing the components, I mean, that's really hard to tell what's going on. You got to be able to see the coordinates here. The coordinates of B, -3, 2, and 3. Got to be able to see those coordinates. And when you look at the vector, it's even more clear what exactly is going on. Okay? Then also determining length when we're talking about something that's in 3D but drawn on a 2-dimensional surface, a length is really hard to tell. Okay? It's kind of like why, Greenland looks enormous compared to Alaska or whatever, when really it's small. When you have it on a map and you're trying to fit something that's 3-dimensional onto like a flat surface, things get distorted lengthwise. So that's why finding the magnitude here is going to be helpful. How do we find the magnitude?
Square root of -4 squared. -2 squared.
Plus what?
5
Good. Plus?
5 squared.
Alright, good. So, the square root of 16 plus 9 plus 25, good, is 50.
5√2.
Good, 5 root 2, which is approximately 2.8. No, sorry, not 2.8. That's only 2 times root 2. 5 times root 2. 7.07.
Yeah.
There we go. Okay? So there's our magnitude. Now we have an idea of how long this thing is. Okay? So, that's it for today. Alright, I want to give you guys some practice working with these. It takes some getting used to working in 3 dimensions. I gave you a few. This is in the IB textbook, so don't turn to your book and go to page 299. Alright? I'm going to export the PDF like I normally do. I'd recommend just getting the PDF and doing them right off of there. Alright, so here, illustrate. So you're doing some graphing just for some practice. Here you're finding vectors and finding magnitudes. A little bit more of that and getting used to language. Then we get into some application. I want you to really focus on these application problems. Show that PQR are vertices of an isosceles triangle. If you don't remember what an isosceles triangle is, look it up. Okay? Here's one as well. Here we have that formula. We had a point 4, 3, -2. We want the vector to be 1, 3, -4. So what would our endpoint end up being? Okay? You got to think through this here. And then some other things. We've talked about unit vectors in the past. Unit vectors are vectors that have what? A magnitude of 1. So, what would k have to be in these cases in order for these to be unit vectors? Okay? So there's some good application problems here that really make you think and really make sure that you understand the terminology and how to use your formulas well. Take the time to really put into these and make sure you're doing them correctly. Okay? Alrighty.